Dobry wieczór. Myślę, że zaczniemy. Już jest parę minut po 6:00. Jak pewnie wszyscy z Państwa zauważyliście, wykład będzie po angielsku. W związku z tym rozpoczniemy wszystko w tym języku. Jeżeli byłyby jakieś pytania, czy w trakcie, czy na koniec, a ktoś by wolał zadać po polsku, czy w jakimśkolwiek innym języku, to śmiało jakoś przetłumaczymy. Mamy specjalistów z różnych języków, poradzimy sobie, dobrze? Także śmiało, jeśli ktoś chce o coś się spytać, to po polsku jak najbardziej. Natomiast wykład jest po angielsku, so let me switch to English and welcome everyone on this magnetic evening. And it's my great pleasure to introduce Professor Vollhardt. He is here for, I don't remember now, 9 or 8 times, and we had a very long collaboration. Professor Vollhardt is from Germany. He is a professor at Augsburg University. This is one of the oldest town in Germany, like 2000 years old. It's close to Munich. But also he worked at many other places. Let me mention a few of them, like Werner Heisenberg Institute in Munich, Technische Hochschule in Aachen. And Aachen, that's interesting because we have a special name for Aachen, Aquisgran. That's the Polish name of Aachen. And finally, he worked in the last 18 years in Augsburg. He did his doctoral thesis in 1979 at Hamburg University and habilitation thesis in 1984 in Technische University of Munich. Professor Vollhardt is a world expert in correlated electron systems, in magnetism, in liquid helium. He wrote a very big book about helium-3 and its properties. And his specialization fits very well to the title of today's talk, and it will be a kind of historical introduction to magnetism. So please go ahead.
Thank you very much. Good evening. Welcome. Can you hear me? Very good. Okay. Well, first of all, I thank the organizers, in particular Professor Bitschuk, for inviting me. It's my great pleasure to be here and to present this public lecture in Warsaw on magnetism, a topic that has fascinated mankind for several thousand years already. Even today, in the 21st century, magnetism has sort of a mysterious sound to it, and in fact it entered our language far beyond its meaning in physics, and I'm also going to talk about that. You may ask, isn't magnetism a very old subject where everything has been known? And the answer is no, because it's not only the horseshoe magnet and an electromotor, but it includes all properties of materials and matter, magnetic materials. So this is a very active research area worldwide. And the question is, what is magnetism? I mean, I try to answer that. Let's do what you do, I guess I do. We go to Wikipedia and sort of find the following. This is not very illuminating, but this is what Wikipedia writes, okay? Magnetism is the class of physical attributes that are mediated by magnetic fields. It goes on for a long time, and then the most familiar effects occur in ferromagnetic materials. Ferro refers to iron because permanent magnetism was first observed in lodestone. Many words. Lodestone, that's a very old word. Lode is an old English word for to attract. And the lodestone is a very old word for a magnetic stone, magnetite. It's actually Fe3O4. But this is all very dry. After all, however, magnetism is something you can experience. There is an invisible force, sort of attraction and repulsion. And let me see whether this movie works because of all the... Should it work? We make a prediction. It works. Okay, good. Yes, this is me. with a little horseshoe magnet and attracting a paperclip. We have all experienced that. Or take a compass. A compass can be influenced by a magnet, and you can even irritate this compass by moving sort of crazy motions. This was attraction, but there could also be repulsion depending on how you approach this bar magnet. There is repulsion and attraction. We are surrounded by magnets. For example, refrigerator door. The refrigerator door itself is held by a magnet. Sometimes we have funny, colorful little magnets on the refrigerator. Then a loudspeaker, certainly a doorbell. Any computer works with magnetism. Mobile phone, as I'm going to explain. Credit cards, TV, handbag. Modern handbags have a magnetic clutch with a very strong magnet. And certainly a car. The more modern the car, the more magnets. Particularly, so such a modern car has about 100 permanent magnets in it, although you would think permanent magnets don't fit into such a modern machine, but that is not so. Now, let's talk a little bit about the early history of magnetism. It is often said that magnetism was first used in China 2,500 before Christ, so that is 4,500 years ago. And in Chinese books, you read that it was the so-called south pointer, a compass, as depicted here. Thing is, there is no written documentation about that, so we cannot really be sure. Clearly, 3,000 years ago, the word magnetite appeared first in Greek writing. And the question is, where does it actually come from, this word? And for that we need to, we refer to Lucretius. He's a very famous philosopher and writer. He wrote the book De Rerum Natura, which you can buy even today now. I read every now and then. He was an extremely intelligent man who was the first natural scientist, so to speak, 2,000 years ago. And he wrote, "The magnet's name the Grecians took from the magnetic region where it was found." So we have to take a look at geography. Okay, so here we are, and here is Greece, and this is Turkey, and in the bordering region is the province Magnesia, where one finds this magnetite, and this is where the name comes from. Magnetite comes either as in these ugly ores or as beautiful crystals. It's Fe3O4, as I said. It's a very common material. It's one of the most commonest materials in the Earth's crust. You find it almost everywhere, particularly if you go to Poland, to the Baltic Sea, to the beaches. I'm sure you find it there. And sometimes you think you're stepping on black sand. It's not black sand, it's magnetite. As you can see, if you take a bigger piece, then you find these little field lines. I'm coming back to that. But also there's a well-known salt mine in Poland where you actually can dig up magnetite. Lucretius, in his book, De Rerum Natura, describes magnetic properties. I read this to you. He wrote, "One has often seen small rings of iron, 6 or 8 or 10, which make a chain without a link between. So great is the lodestone's force." Of course, it was written in Latin. I translated that. Okay? And so this is the first document of an experimental observation in history. And I do this experiment now. I take a little bar magnet. These rings are quite heavy, so I stopped with 5. I couldn't make it 6 or 7. In any case, but it works. So, also known to the Greeks and the Romans were magnetic field lines. If you put a bar magnet on iron filing, you get these field lines. There is a north and a south pole with every magnet. I'm going to explain that. And, if you take 2 bars, you've perhaps seen these, and you put 2 opposite poles next to each other, you have this attraction, you have these typical field lines of the iron filings. If you put equal poles, then you have repulsion and those such field lines. Now, all this was known, but not understood or explained more than 2,000 years ago. And there followed many centuries without further progress at a time when only monks were literate and research was limited to theological considerations. Now, the first technological invention involving magnets was, as I said, the compass. And it was used for navigation. As I said, perhaps it was used already in China much earlier, but there is no documents for that. Clearly, it is documented that as early as 1200, in the Mediterranean Sea, it was used for navigation in ships. So what people did the following. They took a piece of magnetite, stroked over a metal needle, magnetized it, pushed it through a cork, and put it on a water, for example, surface, so to avoid friction. And then it was able to sort of align along north-south and help navigation. Personally, I wouldn't trust my life on this compass, but in principle, it worked like that. And very early experimental work was perfect. This was the first experimental work, apart from Lucretius. Peregrinus in 1269 wrote a book, Epistola de Magnete, where he actually described the construction of a compass, and this comes from this book. He described it in great detail, and I'm sorry, I was given this pointer. I am not used to it. I have to get first used to this pointer. And he also found that a lodestone, a spherical lodestone, has poles. He observed that. Then, 300 years later, the experimentalist Porter did very important experiments. He showed that onions and garlic do not change the poles. I read from his book. It is a common opinion among sailors that onions and garlic oppose the lodestone. Therefore, seamen who are with the captain are forbidden to eat onions and garlic because otherwise they disturb the magnet's poles. But when I tried all these things, I found them to be false. Neither breathing nor licking the lodestone after eating garlic stopped its function. Even when it was all covered with the juice of garlic, it worked as well as if it had not been touched. This is true scientific spirit. This man ate onions, garlic, licked at the lodestone, just to test whether it's true that garlic sort of changes the poles. Of course it didn't. I mean, these captains were clever people. They just didn't want to be surrounded by people with a garlic smell. So they invented this story about garlic changing the poles. Then in 1600, William Gilbert of Colchester published the book De Magnete. Again, you can buy this book today from Dover Publications. It's a wonderful book. And, well, he was Queen Elizabeth's, actually he was a medical doctor and an amateur hobby physicist. And for 17 years, he collected everything, all knowledge on magnetism, which he found trustworthy. And he firmly believed in what we today call the experimental method. He wrote, "Even very intelligent men easily go wrong without experiment and practice." That's very timely. And then in 1600 he published this book, De Magnete. He is sometimes called the father of magnetism. And he also found that, as Peregrinus, that a spherical lodestone, that is, if you make a magnetite round, is a model of Earth. And he said, Earth is a magnet itself. Now, to us today, this is sort of rather natural, but at that time, this was a total revolution. This was very abstract. This was a very daring statement. Now, already in the 17th century, it was noted that magnetism and electricity appear to be connected. I read from a newspaper. In 1681, a ship sailing to Boston was struck by lightning. Observation of the stars showed that the compass was changed. The North Pole was turned south. The ship was steered to Boston with the compass reversed. So what had happened, the lightning had sort of changed the magnetic direction of the compass. There was an interaction between electricity and magnetism. And, but it took another 300 years before actual experimental work was performed to clarify that. And it started with a famous work by the Danish physicist Ørsted. He did the following. He took a battery and a wire and a compass needle, and when there was no current flowing, because there was a gap, then nothing happened. But if he connected the battery and it is closed such that a current flows, he found that the magnetic needle is deflected. And when he reversed the current, then he found that also the needle was changed. So apparently, he concluded, what has happened is that the electric current generates a magnetic field, which then acts on the compass. And further research, he found that the magnetic field around such a straight wire is in concentric circles. So electricity can lead to magnetism. The reverse question is, can magnets also generate electricity? And this was answered by Michael Faraday, one of the greatest experimentalists in the history of physics, in 1831. He performed the following experiment. He used a magnet, a coil, and a compass needle, and when everything was at rest, nothing was moving, compass needle at rest. However, if he pushed this magnet through the coil, then he found that the compass needle rotated. Apparently, this pushing led to a current and then to a magnetic field. And this he called electromagnetic induction. There was an induction of a current through this magnet. And so we learn a magnet and a wire and motion leads to electricity. And since this is a dynamical thing, it is called electrodynamics. Electrodynamics is the name for this whole discipline of moving charges, electricity, and magnets. And there are many applications. You know them all, I guess. As a current generator, you move a magnet, it leads to a current. A steam turbine, you use steam under high pressure, which turns a magnet. The magnet leads to electricity. Or here, a wind turbine, the wind turns these propeller. The propeller is connected to a magnet. It turns, and it leads to an electric field or current. The opposite thing is the electric motor. An electric current can generate a magnetic field, and that the motion of a magnet, the reverse thing, and that can be used attached to a piston, which then turns, is the axle of your motor. This can be extremely big, many thousand tons, but it can be extremely small, also as seen in comparison with a coin here. And, well, an electric motor is also such a limousine. That's also something where electric current leads to motion of a magnet, which sort of turns the piston. And this is a Tesla, for example. Do you know where the name Tesla comes from? Is it an invention? Is it like Phoenix or whatever? Well, no. It's the name of a Serbian physicist who emigrated to the US and made many inventions. And in his honor, the strength of the magnetic field is called Tesla. It's just an invention of industry to call the car Tesla. A little later, all these magnetic phenomena, which had been measured, were put together in theoretical form, in formulation by the famous James Clerk Maxwell, one of the great geniuses in theoretical physics. And he formulated that mathematically in the so-called Maxwell Equations, which describe the entire phenomena of electromagnetism. He was able to solve this, and among others, he found that light is electromagnetic radiation. Today we know that, but at that time it was a shock when it came. Now, there was these equations are just beautiful. Even today we learn them at university level, but there was a problem. The following. In these equations, if you look into these equations, only the relative motion between magnets and conductors appears. This is strange because you would expect that it's a different thing if you move a magnet away from a conductor or a conductor away from the magnet. So this was a question which was open, and let's see. So this was the early 20th century. Let me say an essential stone in the foundations of electromagnetism was missing because this question was open. And this stone was placed by someone whose name is one stone in German. This was Albert Einstein. One stone, playing violin here. In his autobiography, he wrote, "As a child of 4 or 5 years, I experienced a wonder when my father showed me a compass. I can still remember, or at least believe I can remember, that this experience made a deep and lasting impression upon me." And in 1905, he published a paper, article, called Zur Electrodynamik bewegter Körper in German, on the electrodynamics of moving bodies, together with 2 other papers which instantly made him a famous man, still the most famous theoretical physicist. This was the foundation of the theory of relativity. In it, he showed that the Maxwell equations are in fact even relativistically correct. Okay, a lot of physics so far. We need a little break, something more understandable. Love, well, that's not understandable either, but okay, magnetism, emotions, and arts. Magnetism and love, mysterious, have always been mysterious. And so the Romans, in fact, used magnets as amulets. They were sort of carrying it around. They wanted to cure all kinds of rheumatism, gout, loss of hair. They also had little amulets to attract the other opposite sex. You know, they said, well, North Pole, South Pole, man, women, all the same. You know, put the amulet, it will help to find me a lover. And much later, the same Porter who did the garlic and onion experiments actually described the relation between magnetism and love as iron is attracted by the lodestone like a bride by her husband. Okay, you would think that this has changed. Nothing has changed. You go into a perfume store today and you buy Escada magnetism for her and for him. And apparently those who buy it hope to attract the opposite partner, partner. They do not realize, they don't know enough magnetism. They don't know there is also repulsion. You know, perhaps it doesn't work. And then you pay a lot of money for nothing. So this is magnetism and psyche. Let me introduce you to a famous man. His name is Franz Anton Mesmer. Mesmer studied philosophy and medicine, and he developed a hypothesis that what he called a vital magnetic fluid runs through the human body and affects the mood and the health. And he said it can be influenced by magnets. That's why he called it animal magnetism. Today it's sometimes called mesmerism. And Mesmer, he used magnets to heal. He had rich patients coming to him, and he used magnets. Later he left the magnets away because he said he could do it with his hands. Tells us something. And then he had so many patients, they came in groups. So he had to deal with a new situation. So Mesmer invented what is called the magnetic bucket, or the baquet. In it was water, glass, magnetic materials, and he attached to it some wires outside. And so the groups came and held their hands and arms and feet to that, hoping that the magnetic whatever is inside helped them. Mesmer was a man with a very strong personality. He caused trembling and cramps, what is called the mesmeric crisis, in his patients, which sometimes cured them. Today we would refer to that as autosuggestion. But in any case, in many cases, it did something. He also, I'm pushing the wrong button here. He also was able to induce so-called magnetic sleep. And this is the painting by a Polish painter showing this. Patients fall into magnetic sleep. So sometimes Mesmer is called father of high hypnosis. Now, Mesmer had married a rich wife that allowed him to live in luxury and have a great estate in Vienna and become a patron of the arts. And he invited artists, and the Mozart family was also invited to his garden. And a few years later, Wolfgang Amadeus Mozart immortalized Mesmer with his opera, Così fan tutte. I don't know whether you know it. It's musically, it's one of the greatest achievements in music. Text-wise, it's a little difficult, let's put it say. It's also very, there's a lot of love and fake and not understanding. In any case, there is a maid, her name is Despina. She's dressed as a fake doctor and has a piece of magnetite and rubs it over one of the lovers, and she sings, this is Pietra Mesmerica, the mesmeric stone. And by this, Mozart actually made fun of Mesmer and his cure. Okay, let's return back to physics and to the physics of Earth. So, geophysics. The question is, why is Earth a magnet, as Gilbert already said? For that, we need to take a look into the Earth. As you perhaps know, in the core, it's very hot, 3,000 degrees centigrade, and it's solid. I don't know, here, it's solid. Outside, when the pressure is a little less, it is liquid. This is the outer core. Then comes the mantle, and then the thin Earth's crust. In this outer core, where we have liquid means it's molten iron and nickel, and this shows convection. It's like water in a pot. It boils up, and when it cools, it goes down. It goes very slowly, but it's a liquid. It happens even there. And this essentially leads to magnetism. But to understand this better, I have to be a little more detailed. It looks like a big fruit, but this is Earth. So inside we have the solid inner core. Here we have the liquid. And you see this convection of the molten liquid on iron and nickel occurs while Earth is rotating. And the combined action of electrodynamics and magnetism forces the convection along these helical structures, which eventually lead to a magnetic field, to the geomagnetic field, which is quite weak. It's only 1% of a toy magnet. But because this is happening, it's a dynamic thing. It's like the dynamo in the old days of bicycles. Today one has very much more stronger lights. It's called the geodynamo. The geodynamo explains why Earth has a magnetic field due to the convection of liquid metal in the inner parts of the globe. And so if we look at that from outside, the field is surprisingly simple. It is like that of a toy magnet, of a linear magnet with a north and a south pole, two magnetic poles, which allow us to orient us on Earth. We also see that the direction of the magnetic field of this axis is not identical to the rotational axis. So the mechanical rotation of Earth and the magnetic field do not show into the same direction. This is not surprising because they are sort of related but independent of each other. In fact, let us take a look at the position of the magnetic poles here in the north at Arctica and in the south, Antarctica. We see they are not symmetrically placed. In fact, these magnetic poles move, and I just studied this again. The North Pole has started to increase very rapidly in the year 2000 from 15 to 20 kilometers per year, sort of moving around erratically. The magnetic pole in the south is much slower. Nonetheless, it has moved away from the geographic North Poles quite far. And you may justly ask, if it goes away far, can the magnetic field reverse? And the answer is yes. And that has actually happened many times in the history of Earth. How do we know? Well, we take a trip to Hawaii. And Hawaii has many volcanoes. Lava is flowing down and is becoming solid and picks up the magnetic direction of the Earth's magnetic field. Then comes the next eruption, next lava flow, it becomes solid, picks up that magnet. It does that thousands and thousands of times. And this is a diagram as a function of time. Black is up, and white is the other reversed magnetic field. We see there are periods of millions of years where the magnetic field of Earth was stable, and then there are times when it changed very quickly. There have been 150 reversals in 45 years. You're good in calculating, 45 million divided by 150, on average 300,000 years. Last reversal was 800,000. We are long overdue. This is not a good argument, but the next reversal will clearly come. And the question is, when is the next? It will come, and in fact, in the last 100 years, the Earth's magnetic field has considerably decreased by something like 15%. But we can be safe. It will not happen during our lifetime. It takes some time. But it does happen, and you may worry what happens. Is there perhaps a period when there is no magnetic field at all? Because you've perhaps heard, I'm running ahead, there is the solar wind, and perhaps it's bad for us if there is no magnetic field. I found this. Recent computer experiments by Glatzmeyer show the following. Before reversal, let's say in this on Earth, it looks like north-south. Afterwards, the poles are reversed. But in between, for a time of about 500 years, we have 6 poles, and we can have even more. So to have 2 poles is something that occurs very often during the lifetime of Earth, but to have more poles has just as well been realized. It's a fact. And that is good because even during field reversal, there is a magnetic field which protects us. Because as I said, Earth's magnetic field protects us from the so-called solar wind. You know that the sun is very hot and it emits high energy charged particles, the so-called solar wind. And if that would hit the Earth, us, we would suffer. But fortunately, we have the Earth's magnetic field, and this solar wind is deflected by the magnetic field and only enters at the north and the south pole, where magnetic field lines are perpendicular to the globe. This leads, by the way, to something which is called polar light, because the solar wind excites molecules, and you see these wonderful sheets of light, for example, here, and you see it even from outer space. And I took this picture 4 weeks ago. My wife and I, we traveled to Tromsø, which is 400 kilometers north of the polar circle in Norway. My wife also said, I want to see polar light. We went there, we had 3 days. On the first day, we saw that. We were extremely lucky. Okay, we need a break again. So we have a quiz. You are involved. Please tell me what that is. What is this? Okay, I'll make it simpler. It's a gherkin, X-ray. Yeah, could be that. Or it's a lava rock. It's an alien worm, quite probable. Or it's a Bavarian, where I come from. It's a Bavarian. Why? Because this is a Magnetobacterium bavaricum. It occurs quite plentiful in the lakes in Bavaria, particularly at Chiemsee and Ammersee. It's very small. It's, as you see, it's of the order of 1 micron. And it's characterized by these lines, which are strands of very pure magnetite. It's a wonder how nature, in these cool temperatures, produces perfect magnetite. That is a great achievement. And you see, these strands make it a swimming compass needle. They are polarized such that they always go down into the water until they reach the soil and feed and survive. But there's a certain percentage of these which have the wrong polarity. Tough luck. They go into the opposite direction to the surface and die. Ha! But evolution is tricky. Whenever there is a pole reversal, they are the ones that guarantee the survival. So these worms, these bacteria exist for millions of years, have survived hundreds of pole reversals because of this trick. So this is a very small magnet. As a scientist, I would like to ask, is there even a smaller magnet? What is actually the smallest magnet? We do an experiment as we start with a magnet and we cut it in half. So we expect to have a single North Pole then and a single South Pole. To our surprise, we find we have 2 separate magnets which have, again, a North and a South Pole. We try again. Okay, it doesn't work. We always get a perfect little magnet with a North and a South Pole. Now you do that about 20 times or so, and then you arrive on the atomic level. And in fact, an atom, in principle, is a little magnet, because the electron, with its negative charge, is running around the nucleus, which is positive. And this is a purely classical thing which you can understand by classical electrodynamics. This is a small magnet because of this motion. And so we see this is a magnetic pole. Magnetic poles cannot be separated. I should tell you a little story about it. I gave this talk some time ago in the US. When I was at this point, there was a young woman in the first row, and she was showing up and said, yes, what do you want? I'm a single pole. At first I didn't understand. But she said, I'm from Poland and I'm not married. So I'm not making this up. This truly happened to me. Okay. So there are no single poles, at least on the magnetic level. Actually, in fact, there are even smaller magnets because the electron itself is a little magnet with a magnetic direction. It's called the spin. But this can only, in a magnetic field, show up or down, and not like a compass needle in any direction, because it's a quantum particle. The word quantum means it's quantized. In fact, the direction is quantized. It's only up and down. And it is because of these electrons, by the way, that horseshoe magnets are ferromagnets. There are many, one with 24 zeros, electrons in a little horseshoe magnet, and they are the origin of ferromagnetism, as I'm going to explain. But I should also mention that even the nucleus, because it's composed of protons and neutrons, also often has a spin. It depends on the composition. Okay, this having said, we now want to become practical and see how can we make use of it. What is the application of these magnets? This is my first application. This is how I view an early application. Lady tries to get her husband in a uniform with a horseshoe magnet from the beer. In principle, it works, but the lady has to be very strong to carry this horseshoe magnet. I don't think it works, but the compass worked. But let's go into recent times. A novel application is in medicine. It's what is called a magnetic resonance imaging. You take a material where the nucleus has a magnetic direction, put it in a strong magnetic field, apply a small magnetic field perpendicular to it, such that spin tips. That's why it's called a tipping field. And because it tips, it sends out electromagnetic radiation. This radiation goes through our body and picks up the chemical environment, and this can be put as a computer picture. And you have, I'm sure, seen these wonderfully sharp pictures of magnetic resonance imaging, here of a spine and here of a head. Another application is a levitation train, Transrapid, developed originally in Germany. It has no wheels, but only magnets. And it works like this. We take a look into here. So this is this car. Here are two magnets, and they can attract each other. When there is no current, the car sits. When the current is switched on, the two magnets attract each other, and the entire car is lifted up until it's sort of in air. And all you have to do is push it a little. And in fact, only air friction, in principle, it can go with 500 kilometers an hour. Unfortunately, this was never actually commercially done in Germany, but it's commercially done in China for 20 years already. It goes from Shanghai Airport. I see you nod. Perhaps you have taken it yourself. It has transported millions of passengers. It goes from Pudong Airport into town, where it stops, and then you have to take a taxi, which is stupid, you know. But in any case, I took that, and this is the highest velocity. It takes 431, only for 2 minutes. It's a little shaky because the whole train is a little shaky, I have to say. And this is the highest speed. But now China is actually planning to develop a super maglev, which goes even faster with 620 kilometers per hour. These were electromotors, which I discussed. Here I address permanent magnets. What is the strongest permanent magnet? These are so-called neodymium magnets with neodymium, iron, and boron, developed 40 years ago, 1982 in Japan. I'm sure you have seen these all. They are so strong, I personally cannot pick out one of these parts because I have to take some mechanical device. They are about 10,000 times stronger than Earth's magnetic field. And just to illustrate how strong they are, these are very heavy steel spheres, solid steel spheres, which are sort of managed by these very small magnets in between. So these small magnets can lift these big steel shows you how strong they are. These are no toy magnets. If you read the instruction, it says not to be given to persons under 18, because so never give it to children, because what can happen if they swallow it, and there are 2 of these magnets, then in the intestines they may clamp the colon and hurt the colon, leads to lethal injuries. This is a weapon, in fact. And these neodymium magnets are also in your mobile phone. We all have them in the loudspeaker, receiver, in the camera, and whatever. You would think that these modern machines like smartphones don't need anything traditional 2,000 years ago magnets, but no, there are many magnets inside. Okay, so neodymium, we are close to materials. Neodymium magnets is a material, and finally, I want to get at an explanation of how magnetite works. For that, I have to become a little technical, but not too much. We understand the magnetic properties of atoms. There can be non-magnetic atom, and there can be magnetic atoms. Knowing the magnetic structure of an atom, can I say something about the magnetic properties of a material, which is composed of billions and billions of these atoms? That is the question. And we want to understand, can we explain magnetism of magnetite? For that, I have to be now I become sort of a systematic scientist. I show you all types of magnetism. Tonight you can go home and say, I've seen all types of magnetism, really. And I start with material made of non-magnetic atoms. It's called a diamagnetic material. And an example is water. Now you may know we ourselves are made of water mainly, you know. So if you said, I have never seen a diamagnet, show me one, look at your hand. You are a diamagnet. Look next to your neighbor, you're surrounded by diamagnets. And lead and silver are also diamagnetic. And there's an interesting experiment. If you put a diamagnetic material into an external magnetic field, then there is a natural rule that the material wants to oppose it. The diamagnets try to oppose or expel the external magnetic field. So even on the atomic level, there's a repelling force. This is the most natural thing that occurs. Okay, you are perhaps, I tell this story now to the older guys here. So the older guys who have children. Children watch television. You want them to stop. You go into the room, say, children, stop television. They say, no. That is the natural reaction. And this is the natural reaction of a diamagnet. Tries to oppose the external field, leads to a repelling force, and hence you can actually lift a diamagnet by putting it in a strong magnetic field. I show you this here. This is now, you bring a little droplet of water into a strong magnetic field, and it levitates. This is not in outer space. This is here on Earth in the lab. Now you say, haha, if this can be done with water, how about me? Yes, in principle, but let's start small. Let's start with a frog. Put the frog in the magnetic field. It levitates. You may ask, isn't that dangerous? It's not dangerous. It's just the frog is surprised that it levitates. It didn't expect that. It gets a little cold, perhaps, also, but no problem, you know. In principle, okay, so the gravitational force is compensated on the molecular level. This is not science fiction. That can be done in the lab right now. And since it works on the atomic level, it's independent of volume. It can also be done for larger bodies. It's more a technical problem to have a wide magnet with a uniform field. Okay, so the first example was a diamagnet, which was composed of non-magnetic atoms. Now I turn to materials with magnetic atoms. One, if these directions are all disordered, we call it a paramagnetic material, like in air or in molten iron. So then the average of these magnetic directions cancel out. The third possibility is that these magnetic directions all show into the same direction. Then it's called a ferromagnetic material. And the famous example is iron below what we call the Curie temperature. Above the Curie temperature, it is no longer magnetic. Below it is. And neodymium magnets are ferromagnetics. These are permanent magnets. Now watch very carefully. This is the fourth book. Now, this was the ferromagnet. This is the so-called antiferromagnet. Here now, nearest neighbor, the nearest neighbors of each spin have the opposite direction as a nickel oxide. Here again, the magnetic directions cancel out. And now comes the final thing. If you have an antiferromagnet where nearest the magnets are opposite, but they don't have the same size, this is called a ferrimagnetic material. And then this is a permanent magnet because it doesn't average out. Now you say, it's too tedious for me. Do I need to know it? Yes, because this is magnetite. Magnetite, which has been described for 2,000 years, is a really complicated beast. And it is a ferrimagnet. And so it's complicated, in fact, and you need to have quantum mechanics to explain it. And there are many people still working to explain the properties of this substance on which the Greeks already were writing. And this is essentially the end of my talk. No, Warsaw. Okay. The title of my talk was To Modern Warsaw. So I have to, okay. So what's the connection to Warsaw? Okay, so again, this is a little technical, but there is a search worldwide for what is called a dilute magnetic semiconductor. What on earth is that? You have heard about a semiconductor. It's an essential part of every electronic equipment. A semiconductor with a few magnetic atoms is called a dilute magnetic semiconductor. And the goal of this research is to construct one of these semiconductors which are ferromagnetic, because then you could operate a semiconductor with a magnetic field. And this would be, I tell you, this would be $1 billion industry. I'm saying that because very essential work was done here in Warsaw. This is the old building of the physics. This is, we are here. And this man, Professor Jan Guy, he was one of the pioneers here in Warsaw to work on this field. And he actually was also the one who started this seminar series, Ask the Physicist. So with that, I close. I thank you for your attention, and I offer you Ask the Physicist.
For this talk and questions. Pytania? Kto spróbuje pierwszy?
I explained it so well. No, we all know from school and university, not asking questions means two things. Either it was explained so well that everything is understood, the probability is 0, you know? Okay. The other possibility is there are so many questions one doesn't know where to start.
Can you elaborate a little bit on the origin of the Earth's magnetic field? You mentioned that it's caused by the convection of molten iron and nickel in the outer core. And the question is, so what? Are there any electric currents in this? Okay. So it's
well, it's a deep question you're asking, of course. This geodynamo is... Okay. originally it required that there was already a magnetic field. This magnetic field came perhaps 4 billion years ago after Earth was created through the solar wind. And with this perhaps weak magnetic field, which worked as sort of the origin, then comes the convection, which is essentially an electric current, in a magnetic field that was given, plus the motion of Earth, the rotation, because planets that don't have a rotation don't have a magnetic field. And this conspires such, because usually these currents, they're so slow that it would decay. And to have, in fact, such a reinforcing, this regeneration of the current is a very subtle thing. And as we see, it is also very unstable, because otherwise we would always have the same magnetic direction. But we see already that this reversal every couple of 100,000 years means this dynamics is very subtle.
Thank you.
Some other questions? Yes, please.
Could you explain more specifically how were the properties and directions of polarities in these materials of anti-ferromagnetics and ferromagnetics measured?
How do you know that it's a magnet? Yeah.
How do you know that they can be ordered like that to be anti-ferromagnets and ferromagnets?
Well, I suppose, okay, I'm a theorist, but I suppose you can do it by probes like neutron scattering. I mean, you can look into, in fact, you need to investigate the local structure. So you have to look atomistically into the system, and there are experimental methods to do that. For example, by neutron scattering. I suppose there are other techniques to do that. But sort of by looking into the probe, you can do that.
He wrote some question, yes?
Yes.
Okay, so we know that the magnetic poles, they move, but I don't really understand why they move at different speed.
Excuse me, could you?
Why do magnetic poles, why do they move at different speed? The North and the South Pole?
Why do they?
Move at the different speed.
Why
Yeah.
they do? Yeah, because you see, they are sort of, the Earth magnetic field is generated by this complicated giant geodynamo. In principle, it can have even several poles. That shows us that they're quite independent. These poles are not rigidly connected like in this dipolar bar magnet, where, of course, here the North Pole, there the South Pole. But it is something, a dynamic effect inside Earth, which globally leads to a field that looks like a dipole, like this bar magnet, but it is not. It is something, they are more or less on opposite sides, but as you've seen, these computer calculations showed even that the North Poles can be on the side and sort of. The only thing is there must be a North and a South Pole. That's the requirement, because magnets need that, right? But they do not need to be exactly on the opposite side of the globe, because the mechanism that leads to their generation is so complicated, and there is this liquid structure that it is so. And everything inside this Earth is moving, and that leads to the motion of the North and the South Pole. And because they are so far away, they don't talk to each other daily, so to speak. They can move at different speeds. This is the best I can do.
So I wanted to ask you, what is known about this mechanism of the reversal of the dipole, of the Earth's dipole?
Well, this is something which is still being investigated, but the mechanism is, so you ask, why is it unstable?
Yeah.
Right? Why is it unstable? I don't know, and I don't think one knows. These are the results of extremely extensive computer studies which find out, because you need to have a spherical structure, you need to have a non-isotropic composition of your spherical body, and you need to have a regeneration of magnetic field. You have decay, because, I mean, it is, of course, magnetohydrodynamics, which you have to solve together with electrodynamics. And so one was very happy to get the graphics of these field lines from these computer simulations to explain in detail how it goes. I think that is beyond what we can at the moment.
Okay, some other questions?
Hello. I have a question about dilute magnetic semiconductors. What's like current stage of constructing these things? And you mentioned some applications. Can you further elaborate on that? And that's
Okay.
all.
You asked the wrong man, I have to say.
Okay.
Perhaps Professor Bitschuk can reply here. He doesn't work on that, but he sent me information material, and I made it very short. But sort of, what is the current state? Can you say something about that? Simple?
Simple. I understand that there is work going on, and in fact there was a lot of promise about so-called spintronics and that things. Times is going on, and still this is like a promise, not something which was realized. But yeah, but actually also I'm a theoretician, so it's hard to say what is really in laboratories.
There you see, physics, we're experts in our fields. Go to Professor Thomas Dietl. He will tell you. Okay.
Some other questions? Yes?
So in one of those structures where the atoms were the poles, magnetic poles of atoms were the like the same poles put together. There were like plus near plus, and I don't really understand how is it possible for this structure to exist.
I'm afraid I didn't quite. Could you ask the question again, sort of the question, which I can answer? What is the actual sentence with the question?
How is it possible that the atoms turn the same poles to each other?
Did you mean the tipping of the nucleus in a magnetic field?
Mm-hmm. Yes.
Thank you. Yes. Okay. This is unfortunately quantum mechanics. You see, a spin can only show in certain quantized directions, like this. If you tip a field, then depending on the energy that comes in, you can tip the spin so and so much. And on tipping, there is an energy released that goes into the body, so to speak. So you excite, you put energy into the system that flips or tips the spin, and yeah, I don't know. Does that explain? Sort of. You can come to me later if you want a better explanation.
Okay, other?
Hello. I was wondering, because you've talked about the magnetic train in China, and what will happen if you put this train in like void tunnel? Would it be like super speed, or wouldn't like be possible to happen?
This is a big problem. I mean, already when I took this maglev train, which only goes at 431, when it passes a wall, there is just what you say, and even worse if it would go into a tunnel.
Yeah.
there is the danger that the windows break, for example. These are mechanical problems. I think these are big problems. They should never have two trains opposite going, because that would be catastrophic, I suppose. I mean, these are mechanical questions which they have to solve if they want to go at such high speeds. They are aware that this is so, and well, okay, don't build a tunnel.
Okay, thank you.
Okay. Other questions or comments? Yes.
What are the hottest topics in research in magnetism right now?
Hottest, so I have to select one. Okay. Okay, you asked for it. Okay. Okay, there are certain, we are in the age of quantum materials. Materials where the quantum properties are very important to understand the properties. And in particular, also here at the Institute for Theoretical Physics, such materials which live on very strange structures, which are not just square lattice, but they are sort of kagome lattice from Japanese weaving. One would like to know what is the magnetic ground state of electrons or of spins, localized electrons, in such structures. And what is the ground state, for example? What is temperature doing? That is one thing. The other thing, you asked for it, is one would like to understand the topological properties of magnets. There's another buzzword these days, after the Nobel Prize was given to topological properties a couple of years ago. So I limit myself to these things. Certainly, one would always like to have even stronger magnets. That's the technical side. I know little about that. But these quantum materials, their magnetic properties, that's a hot topic.
And maybe I would add, but that's of course open question. You said that there are no single magnetic monopoles, although empirically you learned that single poles can exist. But the question, open question, is about magnetic monopoles as elementary or fundamental particles. Which
Thank you for asking.
Not clear.
This lady in this talk said, "I'm a single pole." So she didn't overrule the laws of nature. The question is still, why to this day has never a single pole be observed, magnetic pole? There is no law that forbids that. The Maxwell equations have no problem. If tomorrow one found a monopole, you just write an additional term in the Maxwell equations, no problem. It would be even nicer because it's more symmetric. And when I was a postdoc, around in the beginning of the 80s, an experimentalist in California supposedly found niobium little spheres, a monopole. Unfortunately, he said he lost it. He put it in a matchbox and it dropped. And okay. And I remember low temperature labs around the world put on their dilution refrigerators to have, well, this goes into detail, to try to find monopoles, to no avail. To this day, no magnetic monopole. There are monopoles in a different context, but they're not the original monopoles. But who knows? It needs only a single monopole in the entire universe to sort of revolutionize things. And we do not understand why there is not a single monopole. It would require a very big theory that shows why this is not so.
Mm-hmm. Okay, other questions, comments? You were very brave for asking so many questions in English, so congratulations. And in such a case, thank you again for this magnetic and great talk.
Thank you very much.
Today.
You were great. Yeah.